Today I'm going to talk about LeetCode question number 207, course schedule. There are a total of num courses you have to take labeled from 0 to num courses minus 1, so this is 0 indexed. You're given an array of prerequisites where prerequisites I is equal to A and B, which indicates that you must take course B first if you want to take course A. For example, the pair 0, 1 indicates that to take course 0, you have to first take course 1. Return true if you can finish all courses, otherwise return false. So for example here, if you want to take course 1, you first have to take course 0, okay? Okay, this course has to be taken first. And for this one, this says to take course 1, you have to take course 0, but to take course 0, you have to take course 1. And as you can see, this is a cycle, right? So we have 1, 0, and then 0, 1. We can't finish these courses because we'll be stuck in a loop here, taking course 1, 0, 1. We can't take either of these courses because both these courses depend on each other. Okay? And seeing this is actually a graph problem where for in A, B, A depends on B, so B is a child of A, okay? To take A, you have to take B first. So how do we detect if we can finish all courses? Well, basically, check if there's a cycle, okay? So our graph can be however many num courses long. But if we find a loop, then that kind of renders us as taking these courses as impossible, okay? Because we won't be able to take course 3 or 2 because we depend on each other. We can't take courses 3 or 2 because they depend on each other. But we have like a kind of a linear relationship here where it's like a graph like 4, 3, or it could be like 1, whatever like that. Then it is possible to take these courses. So basically, it kind of looks like from this prerequisites here, we have to get the order of which we have to take them. And this is a good example of topological sort. Topological sort of a graph is where you get the dependencies first. Is where you sort the graph, where you get the dependencies first and or non-dependencies first and then the dependencies later. So for example here, since 5 depends to take 5, it depends on 4 being taken first. Our topological sort would be 4, 5. Okay, so that's what topological sort is. We take the least dependent components first and then order them by least dependent to most dependent. Okay, so topological sort of 4 and 5 means we can take 4 first. We don't have to take any other course first, but to take 5 we have to take 4 first, and that's how we sorted it. Okay, so this is a good example of topological sort. And yeah. Okay, now to code this up, so what I'm going to do is turn prerequisites into an adjacency list just to make it easier. So that, and it's going to be a dictionary, and it's going to map the node to its children. Okay. So what we're going to do is for I in prerequisites, so if I not in graph, we're going to add it. So graph, I0, since each element in prerequisites is a 2D array. Then graph I0 is going to be equal to a list with only I1 in it. Else, what we're going to do is get children. Append a new child. And then reassign this existing nodes list of children to the updating children list. Okay. So now what I'm going to do is the topological sort, which is O of V plus E runtime, where V is number of nodes and E is number of edges. So topo sort, so I in range num courses. Oh, and before I do that, what I want to do is define my visitin set and visited set. So sets contain O1 our O1 lookup time. So basically, visited, it's easy enough to understand. If we already visited a node, if we already explored a node in our topological sort, then we don't want to explore it again. We don't want to do all that work again. And for visitin, this is kind of important to detect, if we can finish all courses, to detect loops in our graph. Because say we have 0, 1, and then 1, 0, and remember topological sort is basically depth first search. So if we are starting at 0 here, we're put 0 in visitin. Okay, great. And we explore 0's children, which is 1. And then we put that in visitin. Now we're going to explore 1's children. And remember in depth first search, we try to go as deep as we go, as deep as we can in the graph. So then now with 1, let's look at the list of children. Okay, let's visit 0 next. But wait, 0 is already in a visitin list. Well, we're still visiting 0. That means there must be a loop present. Okay, so that's why we have our visitin set here. Okay, and now for the topological sort, so if I range num courses, if I not in visited, what I'm going to do is if topo sort I equals false, then return false. That means we detected a loop. And else, if we made it through all this without having ever returned false, then return true. Okay, now topo sort. This is going to be a helper function that's going to do a depth first search for us. So what's that going to look like? So I'll define that here. That's topo sort. I'm going to take a node. First off, our base case is node in visitin return false. Okay, we found the loop. Or else what we're going to do is if node not in visited, what we're going to do now is get the children, or first off add that to visitin. Okay, we're currently visiting that node, and then get its children. If node has children, so if node in graph, if it has children, then probably like children with the adjacency list. Children equals graph node. Okay. And then for each child in graph, we're gonna go as deep as we can exploring this graph. So we're gonna explore topological sort. We're gonna call topological sort again recursively. Sort child. Okay. And if we detect this child, we're already visiting that child in a recursive call. Then return false. Else, if we make it all through here, then what we're going to do is remove it from visited, add it to visited, and return true. Okay. So let me try running it. Oh, interesting. No, not in visited. Or for child in, sorry. Child in children. Okay, great. Now let me try some other test examples. And I'll submit. Okay, great. Thanks for watching.